So I will now move on to our morning's focal talk presentation by Michael Bennett, titled Automating 35mm Photographic Film Digitization, XY Table Capture System Design and Assessment. And Michael Bennett, who's the head of digital imaging and conservation at the University of Connecticut Libraries, is responsible for digital conversion and conservation operations. And this coordination of conservation and curatorial staff to implement conversion processes requires a really careful assessment of fragile and often oversized materials, something I'm really familiar with in relation to our library's map collection. And that's now one of the first questions we ask, which is, by the way, how big is that thing you want us to image? And this automation of imaging procedures is really important, and it follows very well with Roy's presentation and approach. Sustaining standards and high quality imaging will be outlined very wonderfully well in this talk as well. So I will hand over to you, Michael. Thank you.
Thank you, Fenella. Okay. Okay, well, thank you for that introduction, Fenella. Today I'd like to talk about an automated solution to 35mm photographic film digitization that we recently co-designed and implemented at the University of Connecticut. To begin, let's ask, what do we first think of when we consider 35mm photo film capture? Often the first response is how hard it can be. Then there is the sheer scale of many of our large 35mm collection holdings. Next, there is the format's unique handling considerations, and finally there is the necessary balance between high throughput needs coupled with high spatial resolution requirements. However, beyond the difficulties, what should be remembered is the often priceless visual record that exists on such film, which makes digitization that much more important. So with all of this in mind, we at UConn cast our thoughts to the not too distant past. Back in 2016, we successfully used our large existing XY table to digitize a batch of 9x9 aerial photographic transparencies. The use case then was to help automate the capture of film segments for high-resolution image stitching in post. We knew that although the arrangement ended up working great for 9x9 format, our large XY table's size, ergonomics, and heavy-duty screw drive servo motors were not a good fit for the more precise XY movements needed for consistent high-throughput 35mm capture. But the basic XY engineering was a good starting point for a new, smaller, and lighter design. And here's a list of general specs that we produced for such a design, plus a top schematic view with the table in its far upper left position. Table travel dimensions are particularly important to keep in mind when engineering an XY table's overall structural stability. But these dimensions are also critical for predicting needed floor space to operate the unit once it's installed. Finally, we wanted the system to be multi-purpose and function as a normal medium-sized XY shooting platform when not outfitted specifically to capture film. And here's how that schematic diagram and set of specs were built out in the final installation. You'll note the presence of a few additional components that I'll describe in more detail in a moment. And here's another view of the system from a slightly different angle. And here's that more complete list of system components. I'll go over a few of these in more detail in the next few slides. Of special note is the brain of the system, the Cognisys StackShot 3X, which is the programmable logic controller that controls the table's movements and the camera. To go along with traditional speed, ramp, and dwell time stepper motor parameters, one can use the Cognosys to custom program the table's XY movements to follow a very precise stop-and-go grid pattern in 2D space. This can be leveraged to accommodate the unique but consistent geometries of various film formats and holders. In addition, the controller also allows for synchronized camera control so that both the camera and table work in automated harmony. Here's a quick view of the back of the unit and the 80/20 T-slot structural framing of the system and accompanying tracks with ball bearing carriages. The open builds high torque stepper motor and timing belt shown here power the table's movement along the Y-axis. Here's a view of the Manfrotto three-way pan and tilt head as it's attached to a wall-mounted Kaiser column. The three-way geared head is extremely stable and great for making very fine camera adjustments for alignment with the film plane below. You'll note the Canon 5D SR is paired with the Canon 100mm f2.8 macro lens. This autofocus glass is used in both the table's full auto mode and semi-auto modes, which will make more sense once I get further into this. This shot shows the Zeiss Milvus 100mm f2 lens. Since this lens isn't a true one-to-one macro, you'll notice that I've attached two stacked Canon extension tubes to shorten the lens's normal minimum focus distance. This combination is used in the table's manual mode. To better view the system in action, I've shot and uploaded a brief video to YouTube, which I'd like to show now. However, before I do, I just want to mention a couple of things. This type of high-resolution single-shot photography is very sensitive to motion in either the sensor or the subject. The sounds you hear coming from the camera during the video's initial segment are first the mirror being locked up and held for 2 seconds. This is followed by the lens autofocusing and then the shutter being triggered. I programmed in the mirror lockup and shutter release delay after consistently seeing motion blur in most of our early test shots. This workflow adjustment subsequently solved the camera shake issue. However, I'm still looking forward to one day possibly replacing the current camera with a high-resolution mirrorless body and somewhat simplifying and perhaps speeding up the camera and systems operation. Okay, so how fast does this thing operate? Here are the current throughput rates of the XY system's various modes compared to a traditional Epson film scanner. The 3,900 pixel per inch sampling frequency was determined by filling the Canon 50 megapixel camera and 100 millimeter lens's field of view with the 35 millimeter test target and calculating the resulting pixel density. As can be seen, the XY system can achieve much higher throughput rates compared to a traditional photo scanner. In addition, the camera-based system can also achieve high FADGI performance ratings based upon other objective image quality measures, as will be demonstrated in the following slides. The study's image performance analysis took the general form of comparing the 100 millimeter autofocus Canon and manual focus Zeiss lenses and examining how each affected the overall system. In turn, Image Science Associates 35 millimeter standard black and white film target and Golden Thread software were used in objective data gathering and analysis. And here's what that black and white film target looks like. It includes horizontal and vertical slanted edge features not only in the center of the target, but closer to its four corners, outlined by me here in red. It allows for slanted edge gradient analysis and SFR calculations. And it's a good way to test not only the sweet spot of an imaging system, which is normally the center, but also towards the edges where optical performance can often drop off. We'll take a look at some image performance measures based upon these sampled target regions in a second. First, a few words on methodology. Both lenses were set at near infinity focus while focusing on the film target's center. Shooting distance as measured from the lens's front elements to the subject and camera settings were standardized as much as possible to avoid biasing one lens's performance over the others. Finally, resulting raw files were first processed as black and white positives and then cropped to the same pixel dimensions in Adobe Lightroom. Uncompressed TIFF files were then exported from the application using individual tone curves and sharpening adjustments that follow tolerance ranges as defined in the FADGI guidelines. Golden Thread software was profiled to analyze test images against these highlighted 4-star tolerance ranges, the lone exception being resolution. Indeed, resolution was profiled for 3,500 pixels per inch, which is roughly 3.5 stars according to the currently published guidelines. This decision was based upon what was already understood about the system's highest potential single-shot sampling frequency, or Nyquist frequency, of the 35 millimeter test target. I should add at this point that it was really interesting to hear Don Williams note during his conference talk from yesterday on FADGI's development over time, how this particular 4-star resolution performance level may soon be decreased from 4,000 pixels per inch, as it has come to be seen as unnecessarily high and also mostly unachievable with normal equipment. And according to his related conference paper, which I certainly recommend, he further states, quote, a more reasonable sampling frequency ceiling, that is 4-star, would be 3,000 pixels per inch, end quote. So these are certainly interesting new developments that directly pertain to this study's results, as we'll see in a second. One last note on methodology. There will most likely be some discrepancies between this paper's results and other published MTF figures for these same lenses. Such discrepancies will most likely be due to comparative MTF figures being derived from optical bench testing in a lab. Remember, this XY system was developed to make sharp, detailed, well-formed images and not test lenses necessarily. Additionally, FADGI has specific tolerance range metrics that accommodate the presence of image sharpening. I'll have more on this in a moment when I go over the system's resulting SFR graphs and curves. Okay, so with that disclaimer out of the way, let's look at some general results based upon golden thread analysis. What we discovered was that the system could achieve 3,500 pixels per inch spatial resolution on average across the image field when using either the Canon or the Zeiss lens. We also found that each lens was able to perform at 93% sampling efficiency. This percentage was good for 4-star FADGI. One discrepancy that we found, however, was that the Zeiss had slightly more consistent optical performance across the field of view compared to the Canon. If we think back to those 4-star FADGI metrics from a few slides back, here's how the Canon lens performed according to golden thread. The solid gray bars indicate each slanted edge sampling region's result for spatial resolution, or 10% SFR, which is up here, these gray bars. The top red arrow points to resolution falling 1% below the 3,500 pixel per inch acceptance threshold for the lens's bottom left corner as measured against that region's horizontal slanted edge. Also note the slight variance in lens performance in the other regions as well. The red outline indicates 50% SFR performance within FADGI 4-star range for all sample locations, indicated by the solid black bars. A note of explanation here. 50% SFR values that exceed the tolerance range's upper limit, shown here as a dotted line, are indicators of over-sharpened images, while values less than the range's lower limit, shown as a solid black line, can signal the presence of low contrast or flare. So according to our metrics here, the Canon test image was neither over-sharpened nor too low in contrast. Here's the sample graph for the Zeiss lens. Note this lens is better 10% SFR consistency across all sampled field regions, across all sample image field regions, and its ability to meet the study's 3,500 pixel per inch spatial resolution acceptance threshold across the board. See as well that the 50% SFR lens performance is also within FADGI 4-star tolerance ranges. Let's take another look at these same figures, except this time in the form of SFR curves, where each curve represents a test target region. Again, these are the results for the Canon lens. The top arrows point to the 50% SFR tolerance range, which is delineated by the two vertical dotted lines. Curves that pass through this tolerance range at 0.5 amplitude validate FADGI 4-star acceptance for both image sharpening and any presence of image flare or low contrast. The bottom arrows point to where the curves intersect at 0.1 amplitude, which indicates 10% SFR values and limiting spatial resolution. Note the bottom left region of the image target's horizontal slanted edge illustrated here, with the left purple curve is slightly less than 3,500 pixels per inch. Finally, all SFR curve amplitude levels remain below 1. This additional criterion also confirms a 4-star FADGI acceptance level for sharpening. These are the SFR curves for the Zeiss lens. It similarly meets the same 4-star FADGI tolerances and additionally resolves at 3,500 pixels per inch in all target regions. Note how the curves are slightly more bunched than the Canon's were. This is an indication that the Zeiss is somewhat more optically consistent across its field of view. For those who wish to examine this work in more detail, I've archived the study's complete data set of test images and golden thread reports that may be downloaded from here. In conclusion, both high throughput and high image performance can be achieved with an automated capture system for 35mm black and white photo film digitization. Also, autofocus works consistently well, particularly with high-speed black and white film, where it can easily lock onto grain pattern. In turn, the autofocus Canon 100mm macro can be a high-performing, affordable lens when paired with an automated capture system, such as the XY table. Finally, open modular system designs allow for swapping in of camera and/or sensor and lens upgrades with relative ease as time goes on. Before closing, I'd like to highlight just one example of how we've been able to use the XY system since we've put it into production. Towards the end of last summer, we were asked to complete a rush order of approximately 3,500 black and white 35mm negatives from the library's archives and special collections. These were to be used for curatorial review and selection for 2 print exhibits, including one at the William Benton Museum of Art. Using the automated system and workflows informed by this study's findings, we were able to capture, process, and deliver these images to high FADGI performance levels 30 days ahead of schedule using the labor of a single trained 20-hour-per-week photo technician. And here's one example from that project. I'd like to thank the Yukon Library for their continued support of this research, and Michael Elsacker for his systems integration and design expertise. It was great to develop the system together with these partners. Thank you.
Michael, thank you so much. That was fascinating.